All right, so we're going to continue into our next video, which is about changes to momentum. So the first thing that I want us to acknowledge is that Newton's first law says that unless you have a force acting on the object, that there will be no change to the object's motion. All right, and so they always describe that in terms of velocity, but it's also true of momentum. So imagine I have this bowling ball here, it was in space. I pushed it at some point, right? That's a force that's going to change the object's motion. But now that I'm no longer touching it, this is just a bowling ball going in space. It's going to continue with the exact same speed and it has the same mass. So it's going to continue with the exact same momentum continually forever until something acts on it, all right? So let's imagine we're back on Earth. I've got a nice, let's say that this is ice. I've got a nice icy plane, and I give that bowling ball its push. So now it's moving, and it's traveling, keeping the same speed, keeping the same momentum. If I want to stop it, I need to provide a force in the opposite direction. Remember, I talked about vectors because the directions do matter. So if I provide a force to try to stop it, I need to provide that force in the opposite direction. And I'm going to use that force for a certain amount of time. Now that'll come in a second. But you can imagine, okay, it's going to take a bigger combination of force and time to stop this bowling ball than it would to stop a tennis ball of the same speed, right? If I'm still going to need to apply a force for some amount of time in order to stop this tennis ball, it certainly won't be as much force and time. But I could kind of play with how I want to do it. I can choose to use a fantastically large force for a split second in order to slow down the bowling ball. Or I could choose to use a small force, but just keep providing that force for many seconds in order to stop the bowling ball, all right? This combination of force and time has its own name. It's called impulse. So let's talk through that a little bit. I'm gonna bring the equation that you already knew that I was gonna bring up. F net equals ma. I know, you're excited. A formula for acceleration that we may or may not have talked about, depending on what year I'm teaching you, is acceleration is the change in speed divided by the amount of time it took for us to change that speed. I'm going to imagine that I only had one force, so that simplifies F net just to be F. I can bring this over to the other side. And so let me read this for you. A force acted on an object for a certain amount of time will cause an object to change its speed. An object to change its speed. Now, if I group these together, I can see that that is my formula for momentum. So a change in the mass and the velocity. Now, functionally, it's unlikely that our mass is going to change, but we'll see some situations when it does. But anytime a change happens to the mass or the velocity, that happened because there is a force acting for a certain amount of time. That force for a certain amount of time is called impulse. All right, and so to give us just a description of it, an impulse is like when I push something. So I've got a marker right here. If I push it, I gave it an impulse. I imparted impulse. I imparted momentum when I gave it an impulse. would be a valid way of talking about it. When you provide a force, when you provide an impulse, you are going to give or take away momentum from an object. Okay? Now be aware that that impulse could be the impulse that gives an object momentum, or it could be the impulse that takes away momentum. It could be from a person onto a ball. It could be from, I don't know, a bigger bowling ball onto the bowling ball. Still, there will be a force on this. That force inherently is going to act for some amount of time, which will cause the momentum to change. Sorry, one more thing. With the units for impulse, there's two sets of acceptable units for impulse. One of them would be to say that an impulse changes mass and velocity. So we could still have impulse in kilogram meters per second. So an example might be this starts with 1 kilogram meter per second of momentum, so it was already moving. And then I provide another 6 kilogram meters per second of momentum. So at this stage right here, the bowling ball has 7 kilogram meters per second of momentum, right? I gave it another 6 kilogram meters per second. 6 kilogram meters per second would be the impulse. That would be my original. And so I could say that my original momentum plus the amount of impulse equals my new momentum. Now again, anytime you see me writing a whole word, you're going to probably think, all right, there's probably a symbol that he hasn't told us yet, and there is. Once again, it's an odd one. Impulse is the symbol J. All right? J. At some point, I don't know if you guys have watched The Office, at some point I made the connection that the J and the impulse sounds like Jimpulse, and the P and the momentum sounds like Pam Momentum. Anyway, there's a couple in The Office, Pam and Jim. So Pam Momentum and Jimpulse, if that helps you. All right. I should call it there.